let's see what the effect is when we change the shape of the orbital, okay? Or in terms of quantum numbers, we will change the L quantum number. So just to review, right, if we look at the quantum numbers for what we've looked at before, the 1s and the 2s orbital, what we've done is in the 1s, right, we had a quantum number, a principal quantum number of 1, and L, because it's an s orbital, is going to be 0, okay? And we're not thinking about the m sub L or the spin quantum number right now, okay? We're only concerning ourselves with these two. For the 2s orbital, okay, because it's an s orbital, L is also equal to 0, but, right, the number in front, the principal quantum number, has increased to 2, all right? And then finally, now we're going to change our quantum number L in this case, right? Because while we're maintaining the principal quantum number is 2, L is going to be dictated by the fact that we're in a p orbital, and the value of L is going to be equal to 1. Okay, so we're maintaining between the same principal quantum number, and as we'll discuss later, within the same electron shell, but we're increasing the quantum number L here. All right, so what effect does that have? So let's look at the wave function. So here's the wave function for R2P, all right? And so what we see, again, is a similar sort of organization for the other wave functions we've been looking at, where we have our exponential term and our pre-exponential term. We even still have this, this middle term, which allows for a R2P to be at 0, but this occurs, R2P is at 0 when sigma is equal to 0, which means the radius is equal to 0. And so we already know our wave functions, right? We don't have, we aren't going to have a probability of having electrons at the nucleus. So we don't have anything, we don't expect to have any nodes past the node that we expect at the nucleus, okay? And so what we have is, if we draw this wave function, what this looks like is a little bit wider than the other ones, okay, as far as the peak, right? And again, we see no nodes, right? Again, at any, we see no points of 0 problem, or we see no crossing points of the x-axis in this figure. And so if we, again, look at the probability distribution, everything is squared. Again, we see no evidence of nodes. There's no crossing point here. So there are no nodes, right? And so the nodes, right, the number of nodes we expect the number of radial nodes, I should say, since we were looking at the radial function, is going to be equal to the principal quantum number n minus the angular quantum number L minus 1, okay? And so if we look at this, what we see then, if we look at the nodes for each of these that we've looked at now, right? 1 minus L, n minus L minus 1 is 1 minus 0 minus 1. We would expect 0 nodes, which is what we saw when we looked at the radial function for a 1s orbital. For a 2s orbital, we expect 1 node. And then for a 2p orbital, we expect 0 again, because 2 minus 1 minus 1 is going to be equal to 0. In fact, that's what we see in our radial functions for these orbitals.